You know that classic sound, the wee wee of a siren as it rushes past you? We've all noticed it, right?
Mhm.
That moment, the pitch just seems to drop.
Yeah, it's a really common experience.
Well, today we're going to pull back the curtain on that everyday thing and really dive into the science behind it. We're talking about the Doppler effect.
Exactly. And what might seem like just a funny thing sound does, it actually turns out to be this um, really fundamental principle with huge implications.
Huge implication.
Yeah, so
Okay.
in this deep dive, we're not just going to define it. We want to explore its applications, which are pretty incredible, really, from sound waves right here
hmm
to light that's traveled across, well, vast cosmic distances. You'll see why this idea, which seems simple on the surface, is just crucial in fields like astronomy, but also in tech we use every day.
Okay, so to really get our heads around this, we've looked at some different sources. We've got explanations from physics websites, kind of foundational stuff,
Right.
then some high school physics materials to keep things clear and approachable.
Good idea.
And even checked out some experiments you can apparently do with just your smartphone. So our mission here is to give you, the listener, a really clear, concise, but also engaging picture of the Doppler effect.
Going beyond just the definition.
Exactly, way beyond the textbook line. Show its real-world significance and maybe some surprising sides to it. Okay, let's get into it. What is the Doppler effect, basically?
Okay, so at its core, the Doppler effect is this apparent shift you observe in frequency.
Frequency meaning how often the waves hit you?
Yeah, how many waves pass a point per second. Or you could think of it as a shift in wavelength, which is the distance between the waves. And this shift happens whenever there's relative motion. That's the key term.
Relative motion.
Between the thing making the wave the source and the person observing it. Now, to get a feel for this, picture a little bug just sitting on a calm puddle making ripples.
Okay, got it. Bug, ripples spreading out evenly.
Perfect circles, right?
Yeah.
Someone standing anywhere around sees those ripples arriving at a steady rate, constant frequency. Makes sense. But now, imagine that bug starts swimming in one direction, still making ripples at the same steady pace, mind you.
Okay.
Now, the person standing in front of the bug, where it's heading, they're going to see those ripples getting sort of squished together.
Squished? Why?
Because with each new ripple the bug makes, it's moved a little closer to that observer. So each wave has a slightly shorter distance to travel. They arrive more often. The frequency goes up.
Oh, okay. Shorter travel distance, quicker arrival time, higher frequency. Got it.
Precisely. Now flip it. Think about the person behind the bug, the one it's swimming away from.
Right.
For them, each new ripple starts a bit further away than the last one. So the waves get stretched out. They have further to travel to reach that observer.
So they arrive less often.
Exactly. They arrive less frequently, the frequency goes down.
So longer wavelength, the distance between the peaks is bigger and lower frequency? Okay, so that rising and falling pitch of the ambulance siren, that's exactly this.
That is precisely it, yes. When the siren is coming towards you, it's kind of catching up to the sound waves it's putting out,
And pressing them.
compressing them. Shorter wavelength, higher frequency,
Right.
and your ear hears that as a higher pitch.
Right.
Then, as it passes and moves away, it's moving away from the waves it just sent out, stretching them.
Longer wavelength.
Lower frequency, which you hear is that lower pitch. We even saw some experimental data,
Oh.
where they measured the frequency detected by someone standing still as the sound source moved away at different speeds.
Yeah.
And it showed exactly what you'd expect. As the source speed away from the listener increased, the frequency they measured went down. Clear relationship.
Okay, so higher frequency, higher pitch coming towards you, lower frequency, lower pitch moving away. That relationship between frequency and pitch is key for sound then.
It absolutely is.
Yeah.
Higher frequency is higher pitch for sound.
Yeah.
But what's really interesting, and maybe less obvious, is that this whole effect isn't only about the source moving.
Oh, so it works other ways too.
It does. The Doppler effect also happens if the detector, that's you, the listener, your ear, or maybe a microphone if that's moving, even if the source of the sound is completely stationary.
Really? How does that work?
Well, think about this experiment the sources mentioned. Someone took a smartphone, running one of those frequency meter apps, and just shook it. Just moved the phone back and forth. Even with a steady sound source in the room, like a constant tone playing, just moving the phone.
Yeah.
The detector caused the app to register changes in frequency.
Wow. So if the siren was parked, lights off, but I ran towards it, I'd hear a higher pitch than if I stood still.
That's the principle.
Yeah.
It's the relative motion. That's what matters. Who's moving compared to whom?
Okay, relative motion.
There was another quite spectacular experiment described. Putting a smartphone in a plastic bag.
Okay. Wait, why?
To swing it around safely. Swinging it at arm's length, like a whirligig.
Ah, right.
And if you position yourself so the phone is swinging towards you, then away from you, towards you, away from you, you can actually hear the pitch wavering, going slightly up as it comes closer, slightly down as it moves away.
Huh. I can almost imagine that little nine-yaw sound.
Exactly like that. But here's the clever bit. If the person stood directly in line with the axis of rotation, looking straight down the arm, swinging it, they didn't hear that frequency change. Or at least much less of it.
Why not? It's still moving fast.
Because from that perspective, it wasn't really moving towards or away from them consistently. Its velocity component along the line connecting them was basically zero, assuming a smooth circle. It just highlights, again, it's that direct towards or away motion that really drives the Doppler shift.
That's a really neat way to demonstrate it. Okay, so we've got the concept down qualitatively, but for people who like numbers, can we actually calculate how much the frequency changes for sound?
Oh, absolutely.
Yeah.
There's a formula for it. If you want to quantify the shift, it connects the frequency the listener hears, let's call it FL,
The FL for listener.
to the original frequency the source emits, FS.
FS for source. Got it.
And it also involves the speed of sound, usually called V, and the velocities of the listener, VL, and the source, VS.
Okay, lots of variables. What's the formula look like?
It's FLOL assisted VNIVL. VNAVS.
Whoa, okay. FL equals FS times V plus or minus VL divided by V plus or minus VS. Those plus or minuses. That's the tricky part, right? How do you know which sign to use?
Right, it's all about direction.
Yeah.
Think about the top part first, the numerator, with VL. You use a plus sign if the listener is moving towards the source.
Towards plus. Okay, why?
Because you're running into the waves faster, encountering more of them per second, so higher frequency. Use minus if the listener moves away. You're running away from the waves, encountering fewer.
Okay, listener towards is plus, away is minus in the numerator. What about the source velocity of VS in the denominator?
It's kind of the opposite logic there. If the source is moving towards the listener, you use a minus sign for VS.
Minus. Why does moving towards make the bottom smaller?
Because think of the source chasing its own waves. It emits a wave, moves forward, emits the next one from a closer position. This effectively squishes the waves together. A smaller denominator makes the overall fraction bigger, meaning a higher FL, which is what we expect when the source moves towards us.
Oh, okay. Smaller denominator, bigger result. Makes sense. So source towards is minus.
Right. And if the source moves away from the listener, stretching the waves out, you use a plus sign for VS in the denominator. Bigger denominator, smaller result, lower frequency.
Got it. It really maps directly onto that intuition of waves bunching up or stretching out. And the sources said you can actually measure this with phone apps.
Yeah, it's pretty cool. Apps like PhysiQ they mentioned. Apparently the microphones in modern smartphones are sensitive enough to pick up these frequency shifts quite accurately.
Wow.
You can even do experiments, they suggested, to figure out the speed of something moving just by measuring the Doppler shift in the sound it makes.
That's amazing, using your phone for physics experiments like that.
And, it gets even more accessible. You don't always need an app. The sources also mentioned something called acoustic beats.
Beats? Like drum beats?
No, different kind of beats. Have you ever heard two instruments playing almost the same note, but not quite perfectly in tune, and you get that sort of wah-wah-wah pulsing sound?
Oh, yeah. I know exactly what you mean, when they're slightly off.
That's acoustic beats. It happens because the sound waves from the two slightly different frequencies interfere. Sometimes they add up, sometimes they cancel out. And musicians use this, they've used it for ages, to tune instruments by ear. Trying to eliminate the beats means the frequencies match.
Okay. How does that relate to Doppler?
Well, it's a really neat way to perceive the Doppler effect directly. If you have a stationary sound source playing a tone and another source making almost the same tone is moving, the moving source's frequency will be constantly shifting slightly due to the Doppler effect, right? As it moves towards or away. This tiny continuous shift means its frequency will keep changing relative to the stationary tone.
And that creates beats.
Exactly. You'll hear those wah-wah beats, and the rate of the beating will actually change depending on the relative speed. So in a way, you can hear the Doppler shift happening through the changing beat pattern. No frequency meter needed.
That is clever, using one subtle effect to hear another. Okay, so we've really dug into sound, but you mentioned right at the start this also applies to light.
It does, yes.
Yeah.
Same fundamental idea. Relative motion changes the observed frequency and wavelength.
Well,
But with light, which is an electromagnetic wave,
not a mechanical wave like sound.
right, instead of hearing a change in pitch, we observe a change, usually a very subtle one in everyday life, in the color of the light. Or, more accurately, its position in the electromagnetic spectrum.
Color changes. Like if a car drives past really fast, the taillights look different.
Well, not in a way you'd notice with your eyes day to day. The speed of light is just incredibly fast, so the shifts are tiny unless speeds are enormous, like astronomical speeds.
Ah, okay. So how do we talk about it for light?
We use the terms redshift and blueshift.
Redshift and blueshift. Okay.
When a light source is moving away from you, the observer, the light waves are effectively stretched out, longer wavelength. And the longer wavelength end of the visible spectrum is red, so we call that a redshift.
Moving away, longer waves towards red. Redshift. Got it.
Conversely, if the light source is moving towards you, the waves get compressed, shorter wavelength. The shorter wavelength end of the spectrum is blue, so that's a blue shift.
Moving towards shorter waves, towards blue, blue shift. Okay, same basic idea as sound stretching and compressing, but affecting color or wavelength instead of pitch.
Exactly. And this is huge for astronomy. Absolutely fundamental.
How so?
Think about starlight. It's traveled maybe millions, even billions of years to reach our telescopes. Astronomers can analyze that light very carefully, looking at its spectrum.
The rainbow of colors, basically, but more detailed.
Sort of, yeah. Stars have these unique patterns in their spectra, like fingerprints called spectral lines. They show which elements are present. Now, if astronomers see that whole pattern of lines shifted slightly towards the red end, redshift, that's incredibly strong evidence that the star is moving away from us here on Earth.
Wow.
And not just that the amount of the redshift tells them how fast it's moving away, the sources explicitly mention this observing these spectral lines shifted to longer wavelengths in distant stars is direct proof they're receding. And of course, if they saw a blue shift.
It'd mean the star is moving towards us.
Precisely.
That's genuinely mind-blowing.
Yeah.
Just by looking at the color signature, we can tell if stars billions of light years away are coming or going and how fast.
It is pretty amazing, isn't it? And it goes further. Our whole understanding of the expanding universe, it's built, in large part, on observing redshift. Because when we look at distant galaxies, overwhelmingly we see redshift. Almost everything far away is moving away from us, and the further away it is, generally, the bigger the redshift, meaning the faster it's receding. That strongly suggests the whole fabric of space is expanding.
Wow, okay.
And astronomers even use it to study how galaxies rotate. If you look at a galaxy edge-on, stars on one side will be rotating towards us relative to the center, while stars on the other side are rotating away.
Ah, I see.
So you measure the light from each side. One side will show a slight blue shift compared to the center. The other side a slight red shift. It tells you which way it's spinning, like a cosmic speed trap measuring rotation.
Incredible. So it's like a cosmic speedometer, direction indicator, and rotation detector, all from analyzing light shifts. We started with a siren, and now we're talking about the expansion of the universe and spinning galaxies. That's quite the journey.
It really shows how powerful a fundamental physics principle can be.
Yeah.
And, while the sources we focus on really hit the core concepts in these big astronomical applications, it's worth just quickly mentioning this isn't only about stars and sound waves in theory.
Right. You mentioned everyday tech earlier.
Exactly. The same Doppler effect is used in lots of practical ways down here on Earth.
Like what? Give us some examples closer to home.
Okay, well, radar speed guns the police use. They bounce radio waves, another type of electromagnetic wave, off your car. The gun measures the frequency shift in the reflected waves caused by your car's motion. That shift directly translates to your speed.
Ah, Doppler effect again?
Yep. And weather forecasting relies heavily on Doppler radar.
How does that work?
It sends out radar pulses and measures the shift in the waves that bounce back off raindrops or ice crystals in clouds. This tells meteorologists not just where the rain is, but how the wind is moving within the storm system. Super important for tracking storms, predicting severity.
Okay, that makes sense. Anything else?
Oh, yes. In medicine, there's Doppler ultrasound. It uses sound waves, just like the siren example, but very high-frequency ones. It bounces them off red blood cells to measure how fast blood is flowing through arteries and veins. Helps doctors diagnose blockages, heart conditions, all sorts of things.
Wow. Okay, so speed traps, weather forecasts, checking our blood flow. It really is everywhere once you start looking.
It absolutely is. So just to kind of wrap up our deep dive here, the Doppler effect, it's this apparent change in wave frequency, happens because of relative motion between source and observer.
Applies to sound, applies to light.
Right. Changes pitch for sound, shifts the spectrum redshift or blue shift for light. And as we've seen, it's not just a neat physics curiosity. It helps us understand the universe's expansion, and it powers technology we use constantly.
Yeah, it really changes how you hear that siren, doesn't it? It's not just noise, it's physics in action. That simple pitch change has these, well, profound connections to how we understand the cosmos and how we build useful tools.
It really does bridge the everyday and the cosmic. So maybe a final thought for you, the listener, to take away.
Yeah.
Next time you're out and about, just listen, or even look around. Think about other moving things making sounds, or maybe even fast-moving lights, though that's harder to see. Where else might you be experiencing the Doppler effect without even realizing it? You might be surprised how often it's subtly playing out all around you.